Okay, business algebra, the last section of chapter 3 that we'll cover is on rational functions. Rational functions take two polynomials and divide them, where the denominator is not 0. The most basic rational function is 1 over x, which is sometimes referred to as the reciprocal function, and it has this weird shape here that you see where it curves on either side and it goes way up and down at 0, and that's because as we get really close to 0, we're taking a 1 divided by a really, really small number, which of course is either hugely positive or hugely negative, depending on which side of 0 you're on. Because we're not allowed to divide by 0, this creates what we call an asymptote at 0. Now you'll notice on the left and right side, it also levels off, and that's about the end behavior. Rational functions do not necessarily have the same type of end behavior as polynomials. Let's think about as x gets really big. 1 divided by a really big number is close to 0. Similarly, 1 divided by a really small number, or a large negative number, is also really close to 0. This kind of creates a flattening out on both sides, which creates what we call a horizontal asymptote. And we'll talk about more features as we go and how to find them all in equations before we do any graphing. Okay, 1 over x squared is also a basic graph. What's the difference between 1 over x squared and 1 over x? Well, remember that all terms, when you plug them into x squared, are non-negative. In this case, then we can't divide by 0, so they're all positive. So instead of going down on one side and up on the other, they both go up. A little bit about the domain of the function. So rational functions, any number should be in the domain. The exceptions are places where you divide by 0. We can't put it in the domain because it's not an x value you can plug in if you divide by 0. These domain restrictions usually create holes or asymptotes. Holes are when the numerator and the denominator both share a certain number, 0 over 0. In our case, we're only ever going to look at the asymptotes though. Now, an asymptote isn't part of the actual graph, but it's an imaginary line that we generally use to help us graph, and the graph will approach that line, but never actually touch it. And it's really like a guideline for graphing, and it's caused by a restriction. If the function is going to infinity, that means it's going way up or way down. If the absolute values are going to infinity, as our x value approaches a, so in this case, in the picture above, as x gets close to 0, our function is going way up or way down. The vertical asymptote exists at x equals a. So your vertical asymptote is always a line. It's always x equals some number. And that number should be where your graph is going either way up or way down. Because as you get close to dividing by 0, 1, for example, divided by 1 millionth, as you get close to 0, is a million, which is huge. So that's the idea. A horizontal asymptote is caused by your end behavior. Your function, as you go far left or far right, is approaching a value. Then you have y equals b is the horizontal asymptote. So your horizontal asymptote is a y equals line. You can ignore the slant asymptotes and holes because we won't encounter them. Just know that they are things. If you ever end up switching to a college algebra class, you will encounter them in chapter 3. But for our purposes, we're not going to use them, but they are things that occur, and if you want to know more about them, you can read about them, and if you want to see what some problems would look like with them, just let me know, and we will do some. But generally speaking, let's talk about how we find all of these things. So the vertical asymptote, we said, is where it's caused by dividing by 0. So it's whenever the denominator is 0. So that means usually what we end up having to do is potentially factor our denominator, depending on how complicated it is, and setting those factors equal to 0, like we would do with a quadratic. So not completely unknown, but once those factors are set equal to 0, we get x equals a number for those factors. Those are our vertical asymptotes, and we'll talk about how to graph them later. We'll just focus on finding them now. Again, you could ignore the holes part, but if you ever wanted to find a hole, that would be how you do it. For the horizontal asymptote, in order to have a horizontal asymptote, either your denominator's degree, so the highest exponent you see, has to be bigger than or equal to the numerator's degree. If not, you would have no horizontal asymptote. If your denominator has a larger degree than the numerator, you have a horizontal asymptote at y equals 0. If they're equal, you have a horizontal asymptote at the ratio of the leading coefficients in front of those terms. And we'll see what that looks like in a problem here in a second. So give all vertical, horizontal, and slant oblique asymptotes in any holes. So in our case, we're just doing vertical and horizontal asymptotes and no holes. X plus 7 over x plus 2. So let's start with the vertical asymptote. We take our denominator and set it equal to 0. Which means x equals -2. This line, x equals -2, this is the vertical asymptote. It's not just -2, it's x equals -2. This is an important distinction. Horizontal asymptote. You look at the degrees of the largest powers of x. Y equals x divided by x, which is x divided by x is 1. Now my strategy we'll see in a second is if one of the degrees, if the denominator has a larger value of x, or degree of x than the numerator, write in a 0 x squared or 0 something in the numerator in that case to get an idea. So vertical asymptote x equals -2, horizontal asymptote y equals 1. 3 over x minus 4. Again, vertical asymptote. We set our denominator equal to 0. So x equals 4. Horizontal asymptote. Now, you need to find the matching x term, but there is no x term in the numerator, so sometimes I tell people to write in a 0x. So that when you do this, y equals 0x divided by 1x, when the x's cancel, you get 0 over 1, which is just 0. So this is an explanation for why it's y equals 0 when the numerator is larger, because you just write in the 0 in the numerator, and 0 divided by anything is 0. Let's look at 3 and 4. 3x minus 5 over x squared plus 3x minus 4. The denominator has to factor into x plus 4 and x minus 1. Okay, so vertical asymptotes, you set both of these equal to 0. X plus 4 equals 0. X minus 1 equals 0. So x is -4. X equals 1. So you might be thinking 2. Yes, you can have as many vertical asymptotes as the problem requires, and even ranging from 0, in the event of holes this happens. You probably won't encounter any with 0, to as many as you want, but we're not going to really go past 2 or possibly 3. And the horizontal asymptote, again, the largest power is x squared, but we have no x squared here, so if I put 0x squared divided by x squared, or 1x squared, and they cancel, 0 over 1 is 0. So we have y equals 0 for the horizontal asymptote. Now lastly, let's do 4. If we fully factor everything on 4, we get 2 times x squared plus 4. If I factor the denominator, I'm pretty sure this will be 3x plus 2 and x plus 1. I'll just have to take my word for it for now. Again, vertical asymptote, the denominator is equal to 0, 3x plus 2 equals 0, x plus 1 equals 0. So x is -2/3, or x is -1. For the horizontal asymptote, these do have a matching leading term. So take y equals 2x squared over 3x squared, which reduces to 2/3. So it's y equals 2/3. In the next video, we will look at how we take this information and a little bit more and graph a rational function.